All right, hello everybody, and welcome to another session on our grander topic of geometry. We've talked about actual units of measurement. We're still in that same line, that same reasoning, but we're going to focus today more on symmetry and scaling over the next few topics. Now, I will say this chapter 12 is much bigger than you might think it should be. It's really a couple of topics, subtopics in one. So don't look at more than we've actually covered. It's going to take us a few sessions to get through everything. So just be aware of that so you don't feel too intimidated. Now, the idea of symmetry and scaling, you can see very often in nature. You see the same shapes here, for example, in smaller and larger versions, repeating themselves. Things like the nautilus shell, you see the same shape roughly just appear in larger versions. Now, we're going to try and keep things fairly simple. However, when I talk about scaling, I look at something like this chicken. So let's look at a two-dimensional picture, at least, of the chicken. When I transform the chicken, I want it to have the same proportions as the original. If I think of a height dimension and a horizontal length dimension, this first chicken over here, I've changed the length dimension too much, and the height dimension didn't change. The proportions of the chicken isn't the same. It's not the same chicken. It's not a similar chicken. And in the middle picture here, I've changed the height dimension without changing the length dimension accordingly. The proportions aren't the same anymore. And this chicken, well, he's pretty much the same chicken, but I think he's a little bigger. The proportions are the same. So in other words, we could say the ratio of the original height, or let's say the ratio of the new height to the original height is the same as the ratio of the new length to the original length. All the proportions of the chicken stay the same. Now, in the case of polygons, where we have a little bit more structure, we could actually look at side lengths of the shape, where the chicken is a little bit more curvy. We can talk about similar polygons. Now, don't be too attached to this specific definition, where the interior angles are the same. A consequence of this is that all the proportions are the same. The aspect ratio of the picture is the same. The proportions of new to old side lengths will be the same. Right. So when we talk about changing a polygon or a shape with specific side lengths, and we want to change the length dimension, we are going to refer to that change as the scale factor. Now, I have in this session, I happen to have all the stuff written out already. So the format is going to be a little different than this. Don't be confused with too many things on the screen. I'll try and systematically hide it. But I have everything written down already. I'm just going to talk through it. So the scale factor, when I'm scaling the length, the side length of a polygon, or the height of a chicken, or whatever, a length dimension, it's going to be the ratio of the new side length to the old side length. If I look at these two squares, or really the original square that has a side length of 4 centimeters, I'm transforming it by changing the side length from 4 to 6. I'm not adding 2 centimeters. I am multiplying by a number. To change the 4 to a 6, that number is 1.5. So, whoopsie. Oh, I'll show that in a second. The factor, it's all going to be multiplication. I'm scaling it. It's a multiplicative action that I'm doing, this transformation of scaling by changing the side length. The factor is a ratio of the new side length to the old side length. New side length is 6 centimeters. Old side length original is 4 centimeters. The factor that is involved is 1.5. The side lengths of the square are all changed by a factor of 1.5. And because I'm keeping the proportions of the shape of the figure of the image, this scale factor 1.5 is going to apply to any of the side lengths. It's going to be the same throughout, changing all the length dimensions involved. Okay. So new over old is the scale factor. But now this scale factor, I can definitely use that in my sentence to explain what happened to this square by saying the square changed by a scale factor of 1.5. Okay. But to a certain audience, that might not be clear what I actually did. Often when we're talking about changing things, percentages present a very nice and more intuitive way to convey the concept. So instead of using the scale factor of 1.5 in this example, I want to say it by way of percentages as well. It doesn't change what is happening to the square. It's just how I say it can be a little bit more intuitive to some. So I want to interpret it as a percentage. First of all, I can say, of course, there's a couple of things now I can say that are all equivalent. Like I said, the side length has increased by a factor of 1.5. The 1.5, if I dissect that a little bit, the 1 comes from the original, because if I say the scale factor is 1, then 4 changes to 4. Nothing happens. The fact that the scale factor is greater than 1 means there was an increase in the side lengths. And the increase is really attached to this decimal after the 1, whatever was added to the 1, I'll say. This 0.5 in my example is the change part of the factor. The 1 is really just my base level, keeping the 4, but the 0.5 is making the 4 a little bit bigger. Right? So I'm looking at the change from my base 1, which would have done nothing. If I just multiply here by 1, the 4 stays a 4. But because I multiply by 1.5, I've increased the original length to a new length. So first of all, I can focus on the change amount, and the decimal version corresponding to the change is 0.5. The percentage corresponding to the decimal 0.5 is 50%. So I can say that the side length changed or increased by 50%. Just by looking at the scale factor, we're just saying things in a slightly different way. So I have two sentences that are equivalent and explaining what I did to the square. Side length increased by a factor of 1.5. Side length increased by 50%. Or I can keep the original scale factor as it is, 1.5, and change that to a percentage, which would be 150%, just multiplying by 100. Because 150% is the fraction 150 over 100, which is 1.5. So these things are all equivalent. Random line. All right, so I can say here, the new side length is 150% of the original. So it's all just different ways, equivalent ways to interpret the scale factor, in our case 1.5. I can just say what the scale factor is. I can convert that scale factor directly to a percentage and say the new side length is 150% of the original. Or I can focus on just the change beyond the base 1 the base 100%, and say the side length increased by that percentage, 50% in this case. If I elaborate on that a little bit, and if I look at the change amount from 4 to 6, the change amount is 2, right? This 2 as a percentage of the original 4 is 50%. So you can see here that then again, I'm back to the 50%. So all different kinds of things, or no, it's all the same thing. Different kinds of ways to say those things, to express that information. But it's all built around this scale factor. So let's go to our first exercise, exercise 12.1. Where is that? 12.1. Zoom in a little bit. There we go. In our first, now we're just trying to get used to this. Determine the scale factor in the following cases. Number one, a side length of whatever shape. The aspect ratio is preserved, so I don't need to know every single side. It's changed from 70 to 130 yards. Some field or some area changes like that. So now I have 70 originally, changing to 130 new. That means the scale factor is new over old. See how the units cancel and the scale factor is unitless, 1.86. I can now interpret that for practice by saying various different ways. The scale factor is 1.86. That's one way, of course. I can focus on the increased percentage. It's the old increased by 86%. Or I could focus on the whole scale factor as a percentage, then say the new length is 186% of the old length. All these three are equivalent. And they all refer to the length dimension or how the length dimension has changed. So I'm just trying to get used to that with specific examples. If I look at number 2, the side length changes from 8 centimeters to 5 centimeters. It's our first one where things have actually decreased. Not on this page, on this one. Let's do that first, just show a little bit. So my original old length is 8 centimeters. It changed to 5 centimeters. The scale factor is always new over old, 0.625. In this case, it's down from my base 1, indicating that it was indeed a decrease. Here, I went up from my base 1 because I was increasing the length. So it makes sense that if I'm decreasing it, it keeps doing that. If I'm decreasing it, it makes sense that I should go down from my base 1. By how much? Well, just the difference from 1, 0.375. It's the difference. So now I can use that to express the same information as a percentage. And I can say, just looking at the scale factor directly, the new length is 62.5% of the old. Smaller, right? And if you hear someone say, oh, it's 62.5% of the old, you're thinking, oh, it's a little over half of what the old one was. Yeah, it is. Yeah. Or you can just focus on the decrease specifically. It's down from 1 by 0.375. It's a decrease. The old length decreased by 37.5%. All the same thing. Expressing it in different words, but saying the same thing. So it's very important that I can, of course, first calculate the scale factor. That is, of course, step 1. But after that, and just as important almost, that I can interpret what the scale factor means in various ways using the percentage. Okay, so that was our first step, and we're just changing the length, and by changing the side lengths of the shape, I'm changing the shape, of course. I lost my ability to scroll up and down. Hold on. Oh, there it is. Okay. So we said originally the scale factor is the new length divided by the old length. Perfect. I can rewrite this equation as the scale factor times the old length gives me the new length. So there are three things that have a relationship here: the scale factor, the original length, and the new length dimension. So that means if I have two of the three, I can find the other one. In the first example, the lengths were given and I have to find the scale factor, then I'll use this first version. But maybe a length is given and I want to find another length from the scale factor and a length. So let's see the next exercise. Determine the new side length in the following cases. Few cases there. The original side length of 70 yards is scaled by a factor of 0.9. So then I'll use the second version of the equation because I don't have all the lengths. The new side length is the scale factor that they give me directly applied to times the original 70 yards. Original side length of 70 scaled by a factor of 0.9. So that is as direct as we can get it. Now 7 times 9 is 63, incorporating the decimal and the multiple of 10 there, so I get 63. So it's pretty straightforward if they give it to me in that straightforward of a way. Second one is very similar. The original side length of 70 yards is scaled by a factor of 0.2. There's very little thinking involved. I simply apply the scale factor to the original, and in this case I get 84, because 12 times 7 is 84. So all good so far. But they could give me the information as a percentage. Still very similar. The original side length in number 3 of 70 yards is increased by 10%. Increased by 10%. So then I have to think, well, I have to now make the scale factor. It's an increase, so I'm going to go above 1 by the decimal version of the percentage change, which was 10%. So above 1 by 0.1 or 0.10. I then use that scale factor and apply it to the old original length. Excusing the random line. And I get 77 yards. So there are a couple of things happening here. If I need to perform a calculation involving scale factor, I need to take the percentage and interpret that to the scale factor. I'll never use a percentage in a calculation. A percentage is a presentation option, and that's it. It has no place in a calculation. When I have calculated some stuff and I want to present my answer, then I may want to use percentages as well. Then the last one here, the original side length of 70 yards is decreased by 20%. So now I have to make the scale factor first before I go to a calculation. Now it's a decrease. So from my base, I'm going to go down by the decimal version of the percentage. Percentage is 20, so the decimal version is 0.2. So the scale factor is 0.8. I then apply that scale factor to get the new length in the straightforward multiplication by the original length. 8 times 7, 56. Okay, so I'm just getting used to scale factor and percentages. And how are they linked? How do I interpret them? How do I go back and forth? That is absolutely essential. I'm going to add a fifth question here, a number 5, by just changing the words to number 4 a little bit. And my wording is going to be, the new length is 20% of the original 70 yards. That's not the same as the previous one. The previous one said it's decreased by 20%. That's the change. Now I'm saying the new length is 20%. Many people struggle with that. Those two are not the same. The new length is 20% of the original. That means the scale factor is the decimal version of 20%. 0.2. And the new length is zero point 0.2 times applied to 70 yards. Of course, 2 times 7 is 14. So I have to really be careful and pay attention to how the question is phrased. What words are they using? How are they using those words? Are they talking about percentages? What kind of percentages? Are they talking about an increase or a decreased amount? Are they talking about the new relative to the old? It's all different, and I have to be able to interpret that effectively. Okay, so we've said here, when I change a length dimension, the factor involved, ratio of new versus old, is called the scale factor, and I'm just going to use a K forever. That's going to be my letter that I reserved for scale factor because there's a K sound in scale. I don't know why. It's just first book I read had a K, and you sort of get used to the K, and then using anything else feels weird. Alrighty. So now the question is, okay, first of all, before the question, I'm just going to make a note here that section 12.2.1, the actual transformation of figures, of shapes, we are going to leave until a little bit later. Okay. Okay, so it's the bottom of this page. That's why I was confused here. So don't worry about that section. We are going to do it, just not yet. I just want to finish this conversation in the same with connected things, length and area. So when we talk about area, zoom out so I can see it. That's a little small. Can I not see the whole sentence? The words are cut off a little bit. Oh, I'm so close. I see. Okay. When I talk about area, well, I'm changing the figure, the polygon, by changing the side lengths. So for example, if my scale factor is 1.2, that means if I'm changing if I'm looking at a scale factor of 1.2, for example, that means I'm increasing the side lengths of the polygon by 20%, or a factor of zero point 0.2, giving me a scale factor of 1.2. That's 20% increase in the side length. Does that mean that the area of the polygon, which is now bigger, of course, increased by 20% as well? And if not, how does the area change? Well, let's look at a very simple example by taking this. Just want to change this a little bit like so. There we go. Let's take this little square. That's my original square. And I'm going to transform it. I'm going to scale it by a factor of 3, meaning the side lengths are going to be 3 times what they were originally. So now here I have a 1 by 1 square, and now I have a 3 by 3 square. So the side lengths changed by a factor of 3. I tripled it. However, if I look at the area, the new area is clearly 9 times as much as the original. 9 of these originals can fit in there. So the area doesn't change in the same way as the side length changes, which kind of makes sense because when I talk about area, it has 2 dimensions, the product of the length and the height dimension. And when this square is a 3 by 3 square, the area is 3 times 3. So the scale factor that was involved in the length of the new square is also involved in the height of the new square. It's involved in both and will be featuring twice in the multiplication. So if all the side lengths of the polygon changes by a scale factor of k, then the area of the polygon is going to change by a factor of k squared, because area has the product of these two, and there's a k in both, k times k. Now, I don't want to call this the scale factor again, because I want to, in my mind, separate the two concepts. So I'll just call it the area factor. It's a factor that makes the adjustment in the area, or that refers to an adjustment of area, old versus new. But it's not the scale factor. The scale factor is a term reserved for the length dimension. So I'll call it the area factor. So if the scale factor is k, the area factor is k squared. Let's have an example to just confirm this k squared. Let's just see. Let's look at exercise 12.3. I'm now going to have the luxury of knowing the rectangle's original dimensions, a 50 by 25 rectangle. It's increasing, the side lengths are increased by 50%. So there's my rectangle, my original. The side lengths are increased by 50%. So the scale factor, just like our original example, is 1.5, a 50% increase on top of the base. So because I had the original side lengths, I can calculate the new dimensions of the new rectangle. 50 times 1.5 is 75 meters for the length. 25 times 1.5 is 37.5, the height of the new rectangle, because the side lengths were increased by 50%. That's a scale factor of 1.5. Okay, so far so good. But I now have the dimensions of the new rectangle, so I can calculate the areas. The old area of a rectangle is just length times height, right? 50 times 25. And I get 1,250. We can do it to make sure. Times 25. There it is. The new one, I have the dimensions of that too, so I can calculate the area. I won't always have the dimensions, but this time I'm pretty lucky. New area, 75 times 37.5. Let's see what that is. 75 times 37.5 is. And we can confirm our 2,812. So I'm going to change the question a little bit by not focusing on the change, but trying to get to the new factor between these two quantities. So the percentage of new to old area is new over old, make it a percentage, 225%. We can do it in the chat and see it. 2812.5 divided by 1250 times 100. There it is, 225. Where does this 225 come from? Well, first of all, let me change it to its decimal version, which I divide by 100, and I get 2.25. That is the area factor, right? Because I've compared areas. This area factor is related to the original scale factor. It is the scale factor squared. 1.5 squared, or times itself. 1.5 squared is 2.25. So with this example, I confirm that, oh, the factor that by which the area changes is related to the factor by which the side lengths change. It's the square. of the scale factor. Okay, so I just have to remember this. Scale factor k, area factor k squared. And once I keep track of that, well, now the rest is kind of straightforward. I just have to know, am I talking about side lengths or am I talking about area? Which is which? Let's look at exercise 12.4. The area of a shape is 100 square centimeters. Area. If you want to design the same shape with dimensions 20% larger, what is the new area? What is the scale factor? All kinds of questions. Let's answer everything we can. So we have an area originally 100 square centimeters. We want to change the dimensions and make them 20% larger. So our old area is 100 square centimeters. The side length increase, that's what they said, change the same shape with dimensions, side length, that implies side length 20% larger. So it increases by 20%, all the side lengths, which means my scale factor is 1.2. That refers to how the lengths change, not the area. But I know the relationship between the two. That means the area factor is k squared, which is 1.44. Now I just have to interpret that. So I can say, first thing maybe, the new area is k squared times the old area. Because I'm talking about area, the factor that I use is k squared, which is 1.44, which I apply to the old area, and I get the new area will be 144 square centimeters. That's clearly an increase of 44%. So I can say the new area is 144% of the old, or I can focus my sentence on the change only and say the old area increased by 44%. I didn't actually need to know the size of the original area to talk about the change from old to new. I can just look at this guy, and the change and the percentages are all in there, in the area factor. And the area factor comes from the scale factor, and everything is related. Okay. Takes a while, just let it sink in. It'll be okay. Let's do one more example. Exercise 2.5, 12.5 rather. Very similar, very similar. And then we'll just take a breath and just think about how we feel going into the next session. And leave 12.6. And I'll say in a second what I want to do for 12.6. Let's just finish 12.5. The area of a shape is 50 square centimeters. You want to design the same shape, meaning I use the same scale factor for all the size dimensions, but they're 25% smaller. What's the area of the new shape? And so on and so on. I don't actually need to know what the original area was, but they give it to me. So, old area, 50 square centimeters. They say the length dimension decreased by 25%. That gives me my scale factor by going down from my baseline 1 by the decimal version of the changed percentage. By the change percentage, which is 0.25, so I get 0.75. Then I immediately know what the area factor is. It's k squared. Calculate k squared. MathBot confirms 0.5625. And now it's just a matter of interpreting that. Because I have the actual old area, I can apply it to get the actual new area. It's not a luxury I'll always have. but I do in this case. New area is then the area factor applied to the old area. Area factor is 0.5625. Apply it to 50. Get my new number. Please note, do not ever use a rounded number in a future calculation. If you want to interpret the area factor in a sentence and be done, sure, round away. But if I'm using that, which I am, to calculate something like a new area, use the whole thing exactly. Okay. Next, I can just interpret this area factor to say that, oh, you told me what the length dimension does. It decreases by 25%. The area, however, changes in the following way. Two sentences I can definitely say there, and I want to be able to say both. The new area is 56.25% of the old. It comes right out of the area factor. Or I can focus on the change. Now, yes, the further away I am from the baseline 1, the more easily I can get confused, for sure. So I do have to be careful. This is going down from a baseline 1 by how much? Oh, let MathBot tell me. 1 minus 0.5625. Oh, sorry, two equal signs, right? The gap is 0.4375. So that means the area decreased by 43.75%. Want to be able to do both of these sentences at all times, because I might have to interpret those sentences in a question to be able to extract the factor involved and whatever. Just as I need to make those sentences, I might be required to read and interpret those sentences from a question. So it goes both ways. I just want to be ready. So the goal, whether I talk about length and scale factor, whether I talk about area and area factor, it doesn't change how I interpret percentages. I just talk about length sometimes, or I talk about area some other times. Nothing really changes in how I interpret that factor. But I know that the factors aren't the same between length and area. They are related very closely, not the same. Not the same. Okay, so even though we have the time, perhaps, I want to pause here on purpose so that you can think about or try a little bit in exercise 12.6 to gauge where you're at. Because it is perhaps deceptive to just listen to me. It's like, oh yeah, it sounds good. Area, k squared, yeah, it's all good. Until you have to do it yourself, and then I don't know what, how, So it's very important to sort of self-assess. If you do the whole thing, great. If you do one and you get stuck, also good. Then you know where you're at. And maybe some questions come out of that that you can focus on and we can fix and help. But until you try by yourself, it doesn't always become obvious. So what's the point here? The point is just to have all the combinations of information. Just in a table, forget the words. Different things could be given. I could be straight up given the length area, no, sorry, not area, forget that. The length scale factor as 1.2. Can I interpret that as a percentage change? It's going to be an increase, right? By what percentage? What's the corresponding area factor? What's the corresponding percentage change in the area? So each line is its own question, each row in this table. Or in the second row, I could be given the percentage change in the length. Can I find the others? How do I do that? You have to, any calculation, even k to k squared or k squared to k, any calculation There are no percentages. Percentages is a final concluding sentence presentation format. It is not a calculation format, ever, ever. So if I'm presented with a percentage, I'm going to go to the scale factor before I jump to area. Maybe the area factor is given, and I have to use that to get to the length. Or maybe a percentage is given. But about area, so I need to think for myself here. If for nothing else, to see where I'm at. How well do I understand these things? And if the answer is not at all, well, we're going to have a video. Rewatch the video. That's why we have them. But you need to be able to do it. You need to be able to say everything I just said in this video about scale factor and percentages and interpretation and all those things. So next time we are going to do 12.6, but it's important that you at least try a little. Maybe the whole thing, maybe just one. Spend 5 minutes. It's an investment to see where you're at. All right. Now let's just quickly look at the schedule. And see where we're at here. We are on Friday the 5th. Now, when I made the schedule, I didn't know how people were going to feel, and I just wanted to build in a little break. So Monday will be a Q&A session. Ask something, don't ask anything, do whatever you want with that time. But we'll continue with this 12 point, what was it? I just said it. 12.6, I want to say. 12.6. We'll actually do that on Tuesday, right? The next actual session. That is a live session or a lecture format session. And then we'll tackle the rest of the chapter, actually transforming polygons, which may take us just Wednesday and Tuesday, it may take us more. I don't know. We have enough time. It's just gonna take as long as it takes. And then we're gonna wrap up that part 3. And you see here we have a lot of Q&A sessions in the following week as well. Funny story, I copied the previous semester's calendar and modified it for this one, and you see Remembrance Day made its way all the way through to this semester as well. Obviously, that's not an actual holiday this month. We are just going to have more Q&A time. So the more, the better. Leading us into quiz 3. So with all the question and answer time, there is no excuse to master everything before quiz 3. That is the end. Are there any questions at this time? All right, enjoy the weekend, and thank you.